So I was charged with giving a tutorial on resistivity for non-technical people that may not even know what resistivity is all about or understand the concept. So the scope of my talk is that this is a very rudimentary introduction to the topic of formation resistivity. I'm assuming no previous background or familiarity with formation resistivity and or any geological concepts. So some of you in here may know something about resistivity. I apologize, I'm going to be covering ground that you already know, and there are some of you that are wizards in geology, I'm sure. I'm not a geologist, but I've played one on TV. Also, I assume no formal electrical training other than flipping on the light switch, using jumper cables on your car, pointing the remote at the TV to channel surf, plugging in your headphones to your iPod, you get the message. And when you go to the restaurant and order the appetizer sampler, that could be this talk, okay? So it's not going to go in depth, but we're going to cover, we're going to walk the fences here. So in order to talk about resistivity, in order for us to have a conversation about resistivity, I have to establish some of the vocabulary that nerds like me use when we start talking about resistivity concepts and why we use it. So I'm going to talk about, we have to talk about rocks, we have to talk about porosity, we have to talk about pore space, and I'm going to define a lot of these as we get going. We're going to talk about connate water, we're going to talk about formation water, and I guess we have to talk about oil too, because that's what we're looking for. And we're going to talk about what we're going to talk about, which is resistivity and its reciprocal conductivity, just so you're aware of those that are out there. We'll talk about the different values of water resistivity. Water can be very fresh to very salty, and so we'll talk a little bit about that. We have to talk about voltage and current, and it's impossible to talk about resistivity without some type of mathematics. So I will have to mention Ohm's law, and I'll mention a very basic form of Faraday's law. And I'll define all of these for you so that you'll be able to speak resistivity. Some of you speak Spanish, some of you speak French, English. So when you come out of here, hopefully you'll be able to speak resistivity at some level. So these are some really nice images that I stole from the internet. There's a lot of stuff out there. And so rock A is kind of it's like if you take a microsection, cut it in half, and you're able to highlight the water and the matrix. The black stuff is the rock, and the blue stuff is the water that sits in a pore space. And so we would call that rock because it has a lot of pore space. We'd say that's relatively high porosity, and the porosity is filled with all water, or 100% water saturation is what that will be. The next rock has more black spots in it, so that's more rock matrix, and it's still 100% water, but it's a lower porosity. And then rock C is the same as the rock B, except we've displaced some of the water with some oil. And that's where this is the kind of rock that we're all looking for, right? So if we can draw a schematic of it, we can say that the rock is made up of grains, which is the solid part, or a matrix sometimes it's called, and then you have the pore space. So you see the Greek letter phi down there, that's representative of porosity. So the rock is, if the rock has 20% of the rock is pore space, then 80% of the rock, that 1 minus phi, is rock matrix. If you're up in New England and you're looking at a granite outcrop, that's going to be 100% of the rock is rock matrix. It has no pore space at all. So in the pore space then, you can have different kinds of fluids in the pore space. You can have water, or you can have not water, which not water generally refers to prehistoric decayed organic material. So it's generally oil, hydrocarbon of some sort. I don't know that they found mercury or anything down in the ground in the pore space of rocks, but it could happen, I guess. But generally, the two kinds of fluids are either a water-based substance or a hydrocarbon-based substance. So that's where we talk about that. So water. So there's two kinds of water that that geologists love to talk about, and I don't know who invented this term connate water, but some geologists that wanted to obscure the concept, I guess. But that's prehistoric water. That's fossil water. It's dinosaur snot. I don't know what it is, but it was there when the rock was formed, and it can change its composition over time, but it's old. And then formation water is interstitial water, also called, and it's dripped down in there. It's like the Edwards Aquifer or something like that, you know, groundwater. Goes down into a carbonate formation and makes stalactites and stalagmites. So that's the other kind of formation water. But it doesn't really matter whether it's connate water or formation water. You still got, or interstitial water, you've got to be able to characterize it eventually if you're going to determine how much oil is in the rock. Resistivity and resistance. So resistivity is a material property. And so I can just pick up a lump of material without knowing much about its size, and I could put a meter on it and I could tell you what is its resistivity, because it's a function of the individual particles. It's the inverse of conductivity. So if something was 1 ohm, its conductivity would be 1 Siemens. Okay. And so conductivity, the resistivity is measured in ohm meters. Conductivity is measured in Siemens per meter, Siemens being the inverse of ohms. Now resistance depends on the shape of the material, the rock that you're looking at. So down there is that cylinder. It's got a length A and an area. So I could tell you that volume. Okay, now I can keep that volume constant, and I can make it a long skinny, a small area with a long length, or I can make it a pancake with big area and a short length. Even though the resistivity will stay the same, that letter rho, the resistance will change depending on the shape and the size of what I'm trying to measure. Okay. So this is the electrical resistivities of stuff, because there's a lot of stuff on here. I don't know if you can read it in the back of the room. I stole this off the internet too. So you can see the rocks up top. They're giving us high values. They're giving us 10 to the 12th, 10 to the 14th, 10 to the 4th ohm meters, okay, at room temperature. So what we're really interested, here's petroleum. Petroleum by itself is very resistive, okay? And so that's why if we're trying to compare oil versus salt water, it's actually fairly easy to do. Distilled water is very, very resistive. It's 10 to the 4th, okay? So if you have oil mixed in with distilled water from Walmart, it'll be hard to distinguish the two just on the basis of resistivity. There's other ways to do it, but we're not going to go into that here. Salt water ranges from various concentrations, okay, and that gives you, some good low amounts of resistance. Seawater typically comes in at 0.2. It sits up in here between here. And a hot dog, if you pulled your Oscar Mayer hot dog out of the microwave and it would be about 1 ohm meter is what a hot dog is. And that's why you can heat it up in the microwave, because it has some conductivity there. Resistivity and conductivity. Typical formations, they're looking at clays and shales, they're looking at saltwater sands, oil sands. So everything we're trying to measure is kind of in this range of 0.2 to 10 or 100 ohm meters. If you start to go into to the Middle East or West Texas or whatever, you can get into some fairly high resistivity formations. And you have to have maybe a different kind of tool. You have to have better tool. You have a tool for high resistivity situations, and you have tools for low resistivity situations. I don't know that you'll be able to make that determination after today, but I'm just alerting you that that's out there. This is a salt table that's available from any chart book from Halliburton, Baker, Schlumberger, Weatherford, Pathfinder. And what it shows is that the water, the resistivity of water is like all over the map. It's down here at 0.01 all the way up to 10. So that's, what is that, 0.1, 1, 10, that's 3 orders of magnitude it can vary over, just salty water. And it can even go higher if it's quite pure. So over here you've got this in grains per gallon. So I looked it up. I don't remember this very frequently, but 7,000 grains is a pound. So if you're down here, this is a pound per gallon. And so that gives you a resistivity of 0.1 ohm meters is what that would be. And seawater, which is 0.2, corresponds down here to about just under half a pound per gallon at 3,000 grains per gallon. Mainly the people that use this kind of chart is the guys that are trying to weight up drilling mud, and they need to know the resistivity of the drilling mud as a function of temperature and how much salt they've added into it. So this gives them a way of managing that or determining what its resistivity will be after they've added all the junk they need to add. All right, so now we're getting into some real electrical stuff here, voltage and current. Voltage goes by other names such as electrical potential difference. The Europeans, the French call it tension, electric tension. That's why you get, somebody uses the terms high tension wires. That's high voltage wires, those big fancy wires running overhead. And it's just, I can't explain what a potential difference is. It's really just a difference in energy. Okay, so that energy can be, you can't really, if you could grab an electron and move it through an electric field, you would be creating voltage. But you just have to accept the fact, just trust me, voltage exists. You just put your finger in the light socket and you'll get a very quick lesson on voltage. Okay, and electric current is if I have a voltage and I have infinite resistivity, I have no current. But if I have a voltage and I have a copper wire between these 2 points, then I'm going to have a current flowing between those 2 points on that copper wire. Okay? And so the units of current are amps, the units of voltage are volts. If you're interested further, a volt is a joule per coulomb. A coulomb is an amount of electric charge. So if I have so much charge and I have it at 1 volt, if I have a coulomb of charge and I have 1 volt, that the energy in that coulomb is a joule. Ohm's law, one of my favorite. Ohm's law and Faraday's law. So Ohm's law is very simple. It just says the current through a resistance is linearly proportional to the applied voltage difference. So if this phone is 10 ohms and I have 10 volts across it, I'm going to have an amp flowing through my phone. Okay? If the resistance of this phone is 1 ohm and I have 10 volts, I'm going to have 10 amps flowing through this phone. Faraday's law, so voltage is a way to make currents flow, all right? If I put a voltage across a material with finite resistivity, then it's going to flow current. If it's infinite resistivity, otherwise known as an insulator, no current. Faraday's law is a way of getting current to flow without actually having to contact the formation, actually having to contact the wire or the loop or whatever it is. So I can have a magnetic field. So now I have to postulate the existence of a magnetic field. Okay, we have the Earth's magnetic field. That's a DC, direct current magnetic field. It doesn't change much. But like radio waves, those are very, very rapidly time-varying magnetic fields. Okay, and if I have a loop of wire and I have a time-varying magnetic field through that loop, I will generate a voltage around that loop. And if that loop has some resistance, then I will get current to flow in that loop. So remember that, because I'll show you a picture later on of a logging tool that uses, two logging tools that use that concept. So why is resistivity so important? Okay, I think most of you are probably thinking that it's a plot by electrical engineers to keep themselves employed and everyone else in the dark, right? So, really? No, not really. Yeah. So actually there's this guy, G.E. Archie. He worked for Shell, not Schlumberger, he worked for Shell back in 1942. 10 years before I was born, he developed Archie's relationship. I hope he told his wife, right? Anyway, okay. So the relationship is that water saturation, which is SW, is equal to the square root of a ratio. And that ratio is what we would call R0, which is ohm meters. We're all talking resistivity here. So that blue rock, you know, the rock there with the black bits and the blue water, that's 100% water. So that's what we're going to call R0. And it just so happens that rock is identical to the rock that we have with the oil in it, okay? So we're measuring another piece of rock that has oil in it that's identical to the rock with the blue in it, and we're going to call that RT. So if I take the ratio of the water-filled resistivity divided by the oil-filled resistivity, and I take the square root of that, I can get a percentage of water, okay? So I put just a rudimentary example there. 1 ohm for the water. Say that water sand is 1 ohm meter, and say the oil we've added in there brings that rock resistivity up to 9 ohm meters. Then SW is 1/3, 33%. So the oil, the red stuff, would amount to about 67% of the fluid. Is that good? We found oil! Yay! Money! Can retire. So you might ask yourself, how is R0? How do we calculate the resistivity of that piece of blue rock? Okay, so we have to find, because we can't like flush all the oil out and then put water in there and then figure out what it is. We have to go find a nearby water sand or something, a nearby formation that's like the one where the oil is, and this is the big fudge. We have to then assume, now this guy may be 1,000 feet away, okay? I remember when Pickett was telling me this in my OGCI course, you know, back 30 odd years ago, that, you know, you find this bed, oh, this one's 2,000 or 1,000 feet away, but yeah, somehow magically the water in that bed is the same as the water in the bed that we're trying to evaluate. So, so we have to assume that the RW in the oil-bearing zone is equal to the RW from the nearby water sand, nearby bed. Then in that case, we get R0 equal to some number times that RW. Okay, so I told you, I warned you about porosity. Remember, porosity, I got to talk about porosity now. So this formation factor F, Archie defined as, he had a more general formulation. I'm giving you the 99% rule here. The formation factor is 1 over porosity squared. Now, some of you may be evaluating beds that are a lot more sophisticated than that, or have guys that are doing that, and they have all these cementation and consolidation factors and everything. We're not going there. So anyway, so if the porosity phi happens to equal 31.6%, then my formation factor, conveniently enough, is 10. All right? And I worked with a guy, Jacques Tabanou, who deceased, wow, 3-4 years ago. Anyway, he was a great geologist, log analyst kind of guy. He could wave his hands better than anybody I met. But he had a rule of thumb that if you don't know what the porosity is, or you don't know what the formation factor is, it's 10, okay? So if you're looking at a log and they're giving you RW and you don't really know what porosity is, it's 10. You're not going to be off by more than 30%, okay? So, but yeah, there's a lot of rocks, and if you look at, there's a model that does stacking of spheres and things. So if you have like a random stack of uniform spheres, which is not really rock, but you get like 36% porosity. So it's not far off. You know, most of the world is going to be in the 15 to 25% range. And there's a few weird cases that are down in the 5% range in some of these really strange carbonate formations. But repeat after me. Formation factor is 10. Good. All right, you got something. All right, so then I just take formation factor of 10 times RW, and if RW happens to be 0.10 meter, remember from our resistivity of stuff that we could have water in the range of 0.10 meter, then that means that tool is going to see an R0 for that formation of 1, and then we're going to go up 1,000 feet and we're going to look at our oil sand that's there, and we're going to say, well, if this was fully filled with oil, I'm going to assume the porosities are the same. We got lucky. Then I'm going to say, wow, if that didn't have oil, this would be 1 if it was full of water, and now it has oil and it's reading 9, so I know I've got 66% oil saturation there. So reality check. So now you know why formation resistivity is important and how it can be used, I hope. The rest is just implementation, okay? So you might have guessed, or not, that resistivity tools will fall into 2 classes. Tools can be based on Ohm's law, and there's tools that would be based on Faraday's law. That's really covers the entire world of useful resistivity tools. If it's a real resistivity tool. So sometimes Ohm's law is galvanic or Laterolog. The thing about an Ohm's law tool is you have electrodes that have to then physically pass current or receive current in or out and apply a voltage across the formation in some configuration. And people get really fancy with how they do that because they want to make sure the current's flowing in the formation and not up and down the borehole. Okay, I'm not really focusing on the borehole, but if you have this big if you have this borehole with a lot of conductive mud in it, and you've got an Ohm's law tool, you want to make sure that you're not just measuring the mud, because you could be running, 90% of your current up the borehole, and that's not a good tool. All right. If somebody tries to sell you one of those, throw them out and call me. And there's other tools that are based on Faraday's law, where they would be called the induction tools, wireline induction, or on drill pipe, it's become propagation is the implementation of choice. So the physical principles of all of those tools are very common, and they break down into either Ohm's law, a galvanic type of tool, or they break down into an induction type of tool. And even though we call it propagation, it's still induction. From the transmitter point of view, a little man standing in the rock, he could look at he would see a wireline induction tool and he'd see a propagation tool, and he wouldn't be able to tell the difference, except maybe on frequency, but it's going to be the same physical principle that's out there. So is this an accurate description of where we are right now? Okay, so stole this from, this has been around since the 70s. It's propagated all over the world. It's in lots of textbooks. It originated with Schlumberger in their Log Interpretation Principles and Applications book, sometimes called the Interapps, but so it's kind of fuzzy, but you've got Laterolog, and then an SFL. I'm not going to really focus on the SFL. It's just another kind of Laterolog tool. It's just meant to be a very shallow focus and give you a resistivity close into the borehole without being in the borehole, and it's meant to go with like the induction tools. So these 2 tools, here's a Laterolog 3, is like the most basic building block, and then they got fancy because of all kinds of weird environmental effects, and so they came up with, some genius up in Connecticut came up with the Laterolog 7, and which is a nightmare to design, but anyway. So let's start with the LL3. I did not steal this from the internet. I made it myself, okay? So the LL3 has a measure electrode in the middle here, and out of it comes a current, I0. And really and truly, that's the only current we care about out of this tool. And then you have another electrode down here at the same voltage as this, and you have a guard electrode up above, same voltage as this, and they're all putting current out into the formation. And as you see from these, when you have all these other currents coming out, it's going to focus the middle beam. This is a really lame drawing here, but yeah, it's focusing the current straight out into the rock, which is what you want to do. And what the real purpose of the guard Well, there's two. I guess one is focusing, but the other is if there's a borehole here, I don't want the current from here to go up or down the borehole, because that's not telling me what's out there. That's just telling me what's in the borehole. And I already know what's in the borehole, okay? So once I know this current, and I know the voltage I've put on this thing, so if I have 1 volt on this and I'm getting 1 amp out of this guy, then I can calculate my apparent resistivity. And everybody on these tools, no tool measures RT. All the tools measure something called apparent resistivity, because it's their opinion, and no tools don't have belly buttons, but they all have opinions, and that opinion is called R apparent, okay? And you have to look at it in order to understand if that's really RT, which is what you really want to know on the way to finding oil, okay? And it's just a constant times V over I. You've seen that before, right? What that is, that's just a translation of Ohm's law, okay? So if I pull this over here, I'd have V equals IR. So I0 times R apparent is going to equal K times my measure voltage, Ohm's law, okay? So, but I know V because I'm driving it. I can measure I0, and K is just purely defined by the physical geometry of the tool, and from that I can get an apparent resistivity. Physical properties of the tool. I mean, somebody may get tricky and try to build some borehole or something in there. Generally, anytime you have a number like this, it is derived in a homogeneous formation with no borehole. A really physical condition, right? But the reason they do that philosophically is because if you have multiple resistivities, the only common ground is a infinitely homogeneous medium with no borehole. And then if there is separation or difference of opinion between the tools as to what R apparent is, then you know you have a non-homogeneous situation. And it's that non-homogeneous situation which includes a borehole, which includes invasion, which may include layers or whatever, that then you can invert and figure out what kind of situation you're in. What is your resistivity profile? So that's how the geologists and log analysts all start out. Okay, so that's the LL3, and this is a close-up of the LL7 or dual Laterolog. Okay, and this is a pretty long tool. This guy is 28 feet from top to bottom, and there's a wire line, and they probably run a bridle, which is really just a fancy way of saying they've got a big rubber sleeve over a long length of the wireline cable to keep current from returning so close to the head of the tool. Because the currents come out of the tool, they got to go somewhere, and so they're going to return up top to the closest conductive structure they can find, which is either casing or which is the wireline cable itself. This is a wireline tool. And it has a little pad down here for measuring something called RXO. RXO is another apparent resistivity. This one is meant to be of what we call the invaded zone. I haven't gone there, but you drill a borehole, fluid leaks into the formation. The first foot or two around the borehole, depending on time, gets filled with mud solution, and at that point you get an invaded zone. It's no longer, you've pushed out what was there and you're measuring stuff that you've pushed in there. So a good mud engineer will minimize the amount of invasion by controlling pressure and controlling the chemicals in the mud. No extra charge for that. All right, so the Laterolog is called the dual Laterolog because it has two modes. It has a shallow mode and it has a deep mode. It has all the elements of the LL3, but it's got some other monitors here, and they're using that. Instead of having like a continuous set of electrodes, they put these monitors in there, and the way they adjust their currents is the monitors will work so as to prevent current from going up and down the borehole. So all that's for is to keep the current out of the borehole, make it go straight across. And same thing here. This is just a shorter set of guards. So short guard means your measurement starts to spread out sooner. It's a shallower reading, inspects a smaller volume. This is a deeper guard, more focusing. A longer guard, more focusing, it gives you a deeper range of investigation. Ohm's law tool. So this is a current map from an LL3 type of structure, and this is a short guard. These are the same scale. This is a short guard and this is a long guard, and you can see how the currents here fold back fairly quickly. Over here, by the time they're here, this guy's done, and this guy's still, sending currents out and all that. Okay? Yeah, it looks like this guy's got, well, he's still just as deep as that. Well, it's more than that. It comes out and it fans out a little bit. This is one current line dead center on the electrode. So you have to look at these models, kind of with a grain of salt and really understand what they're telling you. But so the longer guard looks deeper, the shorter guard is a shallower reading measurement. Okay, so now we're getting into the world of Faraday's law. Looks like we're good on time. So this is from 49. This is scribbles from Henry Dahl, who was a really smart guy. And so this is a basic schematic of an induction tool. They have a transmitter, and then they have a receiver. And all he's trying to say is that what happens at the receiver depends on what's in the rock that's in between. And what you get is when this transmitter is got current circulating in it, and it induces currents in the formation. That's Faraday's law. Okay? This tool is not in contact with the formation, not directly. There's no current leaving this tool. All right? The current that flows in the formation originates in the formation, returns to the formation. So I'm not supplying current to the formation from this tool. So the current's flowing in rings, and then, how the more conductive the ring, the more current's going to flow. The less conductive, the more resistive the ring, the less current's going to flow. The less resistive the ring, more current is going to flow. Okay? So that's the basic principle of an induction tool. It induces currents in the formation. It doesn't conduct them, it induces them. Of course, the thing is, once you've established this ring of voltage out here, then the current flows according to Ohm's law. V equals IR. So everything ties together. This is a picture of a section of a propagation resistivity tool. So you have coils. These coils are identified as receivers. This coil is identified as a transmitter. It's a loop of wire wound on a drill collar, and I'm going to put current into it. So that's an ammeter. So I'm going to drive that with current, and then I'm going to measure voltage in these receivers. Now I'm going to measure characteristics of that voltage, such as amplitude, how much is getting here and how much is getting here, and then I'm going to measure the timing, how long does it take for that wave to get here, and how long does it take for that same signal to get here. And I can tell all of that from electrical measurements, which I don't want to go into right now. So that's propagation, but the little man standing out here, I could still draw that little ring of current that sits out here from that transmitter. Okay? And it's going to look the same as it would for an induction tool, the previous slide. This could be a propagation transmitter. This is the ring of current. That's a propagation receiver. So it's all the same. It all ties together. So in fact, what we do, a little bit extra on propagation, because that's probably more relevant to our industry, is we actually have two transmitters, at least two transmitters and two receivers. The tools today have a plurality of transmitter coils now, right? Multiplicity, more than one, more than two. And so you're going to make the measurement from this direction, and then you're going to make the measurement from this direction, and we do that to improve the quality of the measurement to get to implement what we call borehole compensation. So if any of you are familiar with acoustic sonic logging tool, they use the same approach to compensate for variation in borehole and other environmental effects. So no extra charge for that. So here I have my tool, my propagation resistivity tool, and it's sitting in a formation. and the currents are going around and around in that formation, and that's all they do. So if this is high resistive material and this is low resistive material, most of my currents are going to be flowing in this material here, and what I'm going to measure is something called R horizontal. I'm going to get into this in a little bit, just to kind of add something, so you feel like you learned something before you left today. So that brings us into, all right, so that's basically, so I've covered the tool concepts: Laterolog, galvanic, conduction tools. Induction and propagation are based on the Faraday's law, principle of induction. And so is that clear with everybody? So now we're going to talk about, we're going to a formation like this, because I did promise that I would talk a little bit about how can two tools measuring the same piece of rock give different answers. Well, I'm going to show you how the same tool in the same piece of rock can give different answers, okay? And we'll go from then. We'll be ending with that. So I can draw a current through it this way. If I'm coming in, I'm logging this way, I'm going to be driving currents in the plane, right? So my current's going to be flowing in this horizontal direction, if you will. And if I have a way of driving the current this way, then I'm going to get a different reading. So this is called the unit cube, and so if this is a uniform material, I can measure the resistivity this way, or this way, or this way, and I'm going to get the same answer. And all those different, if I'm two opposite planes, are always going to give me the same apparent resistivity. So now I've taken it and I've layered it. If R2 and R1 are different, then the apparent resistivity depends on the direction of measurement. So if I'm this way or this way, I'm going to get the same answer, but if I'm doing it this way, I'm going to get a different answer. I'm going to talk to you about how it's different, okay? So in the green direction, most of the current's going to flow in the low resistivity layers. So assume that's these white layers. So that's where most of the current's going to be flowing, and not much is going to flow in the higher resistive layers. In the yellow direction, which is sort of a series combination of layers, the same current's going to flow through all the layers, and it's these resistive zones that are going to drop the voltage. These layers are not going to drop much voltage, and that's important, and I'll explain why in a bit. So what I have here is I have two situations where I have this tool in this piece of rock flowing the currents this way, and most of it's going to flow in the conductive zones. And then I have, if I drill a horizontal well, I'm going to force the currents now to flow across the bed boundaries. Here the currents are mainly parallel to bed boundaries. Here the currents are flowing across the bed boundaries. Here they're flowing with them, but on the sides they're flowing across those bed boundaries. So I'm forcing current to traverse both the high resistivity and low resistivity zones. And we call this R horizontal, and we'll call that R vertical. R vertical didn't start to come around until we started drilling horizontal wells, and we thought our tools were broken. And then we found a way to say they weren't broken. There is no tool that measures R vertical. I'll just say this here. R vertical is a mathematical calculation to explain what's going on with the tool. R horizontal we can measure. R vertical is a mathematical artifice, okay? So if we have this guy here, we have our unit cube with the layers, and I'm flowing across, then I get kind of all these layers are in parallel. So if this layer was infinite, the easiest way to look at this, say what happens if this layer is infinitely resistive, no current will flow at all, then I'm just basically going from a uniform resistivity of R1, I now have only half of my volume is R1, so I'm going to see an increase in a factor of 2 of the apparent resistivity, and that's all this is saying. Forget all this, okay? But it's going to say basically my conductive elements are going to dominate, and how much volume they have, that's what I'm going to see. So if I cut my volume in half, I'm going to double my apparent resistivity. In the case where they flow vertically, now I've got everything in series, then I can just add everything together, and what I've got is I would really like to focus on this guy, these can't be infinite anymore. I'm just going to measure infinite resistivity. So say these are 100 and the other ones are 1, then I'm going to measure half of my volume is this resistive stuff and the other half is insignificant. Okay? So then I'm going to end up with half of the 100 or 50 ohm meters is what that's going to be. So there's that same piece of rock. If I measure it this way, I get 2 ohm meters. If I measure it this way, I get 50 ohm meters. Okay? So the salesman from the logging company is not full of crap. He's actually telling you the truth. Just thought I'd throw that in. Okay. Layered formations. In layered formation, the direction of the current flow is important. When the current flows parallel to the bed boundaries, or what the geological guys, the rock guys, would call stratigraphic bedding. Ooh, that's cool. You know, go on a date. Hey, we're going to go look at some stratigraphic bedding. Yeah. Then the low resistivity layers will dominate, and the high resistivity layers are less important. When the current flows perpendicular to the stratigraphic bedding, the high resistivity layers dominate. Okay, or it boosts everything up. So that this phenomena is referred to sometimes as resistivity. I didn't define this. I guess I can't tell you what it is. Sorry. Okay. So what that was is resistivity anisotropy. Okay. A-N-I-S-O-T-R-O-P-P-I. T-R-O-P-Y. Anisotropy. And it's really fun to watch people try and pronounce that, because they want to say anisotropy or something. You know, you got to put the right emphasis on the correct syllable there. All right, well, that's the end. That's all I have. Thank you for your attention. And did you leave me any dessert? so.